So my name is Omer. I'm going to talk about client-server concurrent zero-knowledge with constant rounds and guaranteed complexity. And this is a work with Canetti and Abhishek Jain. So our subject today is zero-knowledge protocol. So let me start with some quick definitions. So a zero-knowledge protocol is an interactive proof system that allows a prover to convince a verifier of the validity of some NP statement. And this protocol should satisfy three requirements: completeness, soundness, and zero-knowledge. So completeness means that if the statement is true and the prover has a valid witness, then it can always convince the verifier to accept. Soundness means that if the statement is false, then no cheating prover can convince the verifier to accept with more than negligible probability. And finally, the zero-knowledge requirement says that a cheating verifier cannot learn anything from interacting with the honest prover on a true statement. And we formalize this by requiring that the view of the verifier in this interaction can be simulated by an efficient simulator that does not have access to the witness. So zero-knowledge is an extremely fundamental object in cryptography. We want to understand zero-knowledge protocol, first of all, because it's a really fascinating notion, but also because we often use zero-knowledge as a sub-protocol when constructing some larger cryptographic protocol or system. So one of the central things we want to understand about zero-knowledge is what happens to the security of zero-knowledge protocols when we compose them together with other protocols. So maybe one of the most natural forms of composition is what we call concurrent self-composition. So here we have many copies of the same zero-knowledge protocol running concurrently to each other. And in all of these executions, the prover is using either the same witness or more generally, witnesses that are somehow related. So every one of these concurrent executions is called a session. And now the security requirement is that even a cheating verifier that can participate in many concurrent sessions and can arbitrarily control the scheduling of messages in all of these sessions still cannot learn anything from this interaction. And again, this is formalized by saying that the view of this concurrent verifier in all the sessions can be simulated by an efficient simulator. So it turns out that constructing concurrent zero-knowledge protocols is much more difficult than plain standalone zero-knowledge. So to see that, let's compare the state of the art. So we have standalone zero-knowledge protocols with 4 rounds based on any one-way function. But to get concurrent zero-knowledge, we'll need to compromise either in the round complexity or in the assumptions. So we have concurrent zero-knowledge based on one-way functions, but with logarithmic round complexity. And recently, we were also able to get constant round protocols. But these are based on very strong assumptions that are still kind of far from being well understood. So in this work, we do want to get constant round protocols based on standard assumptions. And the way we do it is by considering slightly weaker notions of concurrent security. So to motivate our result, let me start by presenting 2 existing notions. So the first notion I want to talk about is bounded concurrent zero-knowledge. So if before we wanted security against an arbitrary polynomial number of concurrent executions, in bounded concurrent zero-knowledge, there is some a priori fixed bound on the number of sessions. So Barak showed that assuming collision-resistant hash function, there is a constant round bounded concurrent zero-knowledge protocol for every bound B. And the communication complexity of this protocol will be polynomial in the bound B. So in Barak's protocol, the number of concurrent sessions needs to be set at protocol design time. And in some settings, this turns out to be a serious limitation. So consider, for example, an internet server that wants to give zero-knowledge proofs to many clients using Barak's protocol. So now, before the protocol starts, the server may not know exactly how many clients are going to connect. So now the server has a problem. On the one hand, if it set this bound too high, then it pays for it in the communication complexity of every single session. On the other hand, if it sets the bound too low, then it may need to reject some clients that want to connect in order to preserve the security. So the next work that I'll talk about is the work by Persiano and Visconti that is dealing exactly with this limitation. And the idea of Persiano and Visconti is somehow to allow the server to dynamically change this bound on the number of concurrent sessions during the protocol execution. And to do that, Persiano and Visconti introduce a new model for concurrent zero-knowledge. So as you recall, in the standard model of concurrent zero-knowledge, we require that the honest provers operate completely independently in all the different sessions. And now Persiano and Visconti suggest a slightly different model that we will call the client-server model, where there's a single server controlling the honest prover in all the sessions. And this server may introduce some correlations between the different executions. So of course, we don't require that all the executions of this protocol in the world are running from a single server. We only care about related executions, executions where the honest prover is using either the same witness or witnesses that are somehow related. Now, in general, introducing correlations between different sessions is a bad idea. It's bad for the server because it makes it more complicated to implement, and it's also bad for the clients because clients usually don't care about each other, and no client wants their session to be affected by some other session. So the idea is to only introduce very mild correlations that will not complicate the server too much and will only have a minimal effect on the clients. Specifically, the suggestion of Persiano and Visconti is a protocol where the server just needs to count the number of active concurrent sessions, and it's allowed to increase the communication complexity of every session as the number of active sessions increases. So very roughly, what the protocol of Persiano and Visconti does is that in every session, it runs Barak bounded concurrent protocol many times sequentially, each time increasing the bound on the number of concurrent sessions. So they start by running Barak's bounded concurrent protocol with a bound of n sessions, and then n squared sessions, and n cubed, and so on, until at some point, the bound exceeds the number of active concurrent sessions, and then the protocol can terminate. So let's see what's the complexity of this protocol. So if we have n to the c concurrent sessions, then the round complexity of every session will be at most order c, because we need to run Barak's protocol at most c times. And the communication complexity of every session is dominated by the last bounded concurrent execution we have, so it will be polynomial in n to the c. So this looks very good. We get almost the same complexity as Barak's protocol, except that the round complexity is not constant. It's growing very slowly as a function of the number of concurrent sessions. But now the advantage of this protocol over the bounded concurrent protocol is that this protocol is fully concurrent. There is no a priori bound on the number of sessions we can execute. OK, so in the protocol of Persiano and Visconti, the communication complexity is changing at protocol runtime. So from the point of view of the server, this is good because now the server doesn't need to set any bounds ahead of time. But from the point of view of the client, this can be very problematic because now the client has no idea what is going to be the communication complexity of the protocol. In fact, the client may not even know if it has enough resources to finish the session. The server may keep increasing the communication complexity until at some point the client just has to give up and abort. So this is exactly the problem that we want to solve today. And before I'll tell you about our solution, let me give another example for completely different settings where we have exactly the same problem. So imagine that you're placing a call to a call center, and you hear the following very familiar message. All our lines are currently busy. Please hold, and your call will be answered shortly. So now you really have no idea how long you're going to wait. And this can make your waiting very unpleasant or sometimes unpractical. So the solution here is very simple. The call center should just tell you what's the estimated wait time in the beginning of the call. So this will make your waiting much more pleasant. And also, if this time is too high for you, you can just hang up immediately, right? So in our settings, we're talking about communication complexity rather than wait time. But the solution is going to be exactly the same. So we suggest a protocol where the communication complexity of every session is set at the beginning of the session, and it never changes. So we call this feature guaranteed complexity. So now let me tell you about our result. So we show that assuming collision-resistant hash functions, there is a concurrent zero-knowledge protocol in the client-server model with constant rounds and guaranteed complexity. And again, guaranteed complexity means that the server needs to commit to the communication complexity of every session at the beginning of the session. Okay, so let me just quickly summarize the differences between our protocol and the protocol of Persiano and Visconti. So in terms of round complexity, we have constant rounds, whereas in the protocol of Persiano and Visconti, the round complexity grows with the number of concurrent sessions. And in terms of communication complexity, in both cases, it grows with the number of concurrent sessions. But in our protocol, the complexity is determined at the beginning of the session. And in the protocol of Persiano and Visconti, the communication complexity of every session is not determined until the session terminates. OK, so let's go on and describe our protocol. So the protocol is going to be extremely simple. Every session is just going to run Barak's bounded concurrent protocol with some bound. And the way we set this bound only depends on the order in which the sessions start. Specifically, the first n sessions to start will run Barak's protocol with a bound of n sessions. The following n squared minus n sessions to start will run Barak's protocol with a bound of n squared sessions. The next n cubed minus n squared session will use a bound of n cubed, and so on. So note that the communication complexity of every session only depends on this bound, so we can really set it at the beginning of the session and never change it. Okay, so before we start with the security proof, let me just tell you what's the main challenge in proving that our protocol is secure. So the main challenge is that we only took into account the orders in which the sessions start, but we have no idea how the rest of the scheduling looks like. Specifically, it could be that the first session to start is also the last one to terminate. And now, according to our protocol, the first session is running Barak's bounded concurrent protocol with a bound of n sessions. But now the number of sessions that can start concurrently to this session may be much larger than n. And remember that now the prover is already committed to the communication complexity of the first session. It cannot increase it like in the protocol of Persiano and Visconti. So really, the challenge is how to reduce the security of our protocol to the security of the bounded concurrent protocol. So our security proof is only going to use Barak's protocol mostly as a black box. But there is one fact about the simulation of Barak's protocol that will be important for us. So Barak's protocol is bounded concurrent. So there's a simulator that can simulate the view of a verifier that participates in at most B sessions. Now, you can think about the simulator as operating separately in the different sessions. And when we simulate, for example, the first session, the simulator really doesn't care what's going on in all the other sessions. It only cares about the communication complexity of the other sessions. In fact, we could simulate the first session, even if all the other sessions are running some arbitrary different protocol, as long as the communication complexity of this other protocol is smaller than the complexity of Barak's protocol. OK, so this is really the one picture you need to remember about Barak's protocol. So now let's start with the security proof of our protocol. And we'll start with some very simple terminology. So we say that a session is of level I if it runs Barak's protocol with a bound of n to the I sessions. So now our first observation is that if the verifier starts at most n to the c sessions, then sessions of the highest level, level C, will always be easy to simulate, because these sessions run Barak's protocol with a bound that is sufficiently high. So we may not know how to simulate sessions of level 1, for example, but simulating sessions of the highest level is always easy. So now let's consider some arbitrary execution that contains sessions of all levels, level C, C-1, C-2, and so on. And now, as we said, we can simulate sessions of the highest level. So we have this partial simulator, S0, that only simulates sessions of level C and forwards all the other session to some external prover. Okay. So this is just the simulator of Barak that we discussed before. Okay. So now the main idea of the proof is to just think about this partial simulator as just another concurrent verifier for our proof system that only starts sessions of level C-1 and lower. So by the same arguments as we had before, there is another partial simulator, S1, that again can simulate sessions only of the highest level, which is now C-1. And again, all the lower level sessions are being forwarded to an external prover. And now we can repeat this process many times. And after at most C iterations, there will be no more sessions that are being forwarded out. And this means that we actually simulated the entire interaction. So there is one last point that we need to pay attention to, which is the running time of the simulator. So the running time of the partial simulator S0 is polynomial in the running time of the verifier. This just follows from Barak's simulation. Similarly, the running time of S1 is polynomial in the running time of S0, and so on. And since the number of iterations is at most constant, then overall the running time of our simulator will be polynomial. So that's what I wanted to say. Thank you very much.